This video is going to talk about the standard cell potential. So when we're talking about standard, we simply mean standard conditions, and that's what this naught represents. So that would be 1 atmosphere for all of your gases, 1 molar concentration for any solutions, and typically it's a temperature of 25 degrees Celsius. The cell potential, this term describes a species, so that could be like an ion or an element, a species pull on electrons. So how much pull an element or an ion has for electrons. And when you're looking at the different half reactions, like the reduction or the oxidation half reaction, the cell potential is compared to the She that we talked about in the POGL, the standard hydrogen electrode. And when you take both of those and you add them together, you'll get the overall standard cell potential for that particular electrochemical cell. And that is measured in a unit of volts. We'll do an example of calculating standard cell potential for a galvanic cell. So remember that value has to be a positive cell potential if we're talking about a galvanic cell. And here are your components. You have a nickel electrode, you have a solid silver electrode, then you have some nickel 2 nitrate, and you have some silver nitrate. And those would both be 1 molar. We're at standard conditions, aqueous solutions. You'd also have materials for a salt bridge and containers like beakers. So why don't you copy down the problem, pause the video, and then draw your setup for your electrochemical cell. And then we'll figure out the directions of the electron flow. Okay, so hopefully you have a sketch that sort of looks like this. It doesn't matter what side the silver cell is on versus the nickel. That's fine. You should have a salt bridge, which I have in orange. It should be dipping below the liquid, the aqueous levels. You should have a wire that's connecting your 2 electrodes. Right here is where I'm going to display my cell potential once I figure it out. There are lots of silver ions floating around. I just didn't have room. And there are lots of nickel 2 plus ions floating around. I just didn't have room. Our next step is going to be to look at our reference sheet. Here we have standard reduction potentials. So every half reaction that's on here is going to be a reduction. So it's going to show a gain of electrons. And then the cell potential that's associated with that specific half reaction when compared to the She, the standard hydrogen electrode. Some of them are going to be positive, and then some of them are going to be negative. You can get the oxidation potential simply by flipping this sign to make it an oxidation half reaction. Flipping the arrow and then also flipping the sign for the potential, okay? And then that will make it an oxidation potential. So if your reduction potential is positive, you're going to make it negative if you want an oxidation potential. And if your reduction potential is negative, you're going to make it positive. So you just switch the sign to make it an oxidation potential. So let's take a look at what we're dealing with here. If I look down this list, I find one of my half reactions, the silver, and if I look a little further down, I can find the nickel. Okay, so what becomes important is where these things are located. Whichever one is higher, and we'll write this down in just a second, but whichever one is higher, that's the one that's going to naturally or spontaneously be reduced. So it looks like our silver ion is going to gain the electrons, and that means that the nickel metal will have to give up the electrons. So this guy will be oxidized. So what we're going to have to do for the oxidation is switch this direction of the reaction and then also switch the sign here. So instead of writing down the oxidation potential as negative 0.25, it's going to be positive 0.25. So here are some notes that reiterate what I just said. The more positive reduction potential, that's going to be associated with your reduction half reaction if you're trying to see what happens spontaneously. And then for the less positive, that's going to be your oxidation half reaction. In order to get the oxidation potential, you're going to need to switch the sign. And then one other note, you never multiply your reduction or your oxidation potentials by anything. So when you're balancing a redox reaction, you have to multiply through to make sure you have the same number of moles of electrons. We don't have to do that in this case when you're just adding up the oxidation and reduction potentials. So now it's time to actually calculate the cell potential. I just pulled our reference sheet back down so that we can remember these values. So the reduction potential from right here is going to be 0.80 volts for the silver half reaction, and then the oxidation potential from right here is not going to be negative 0.25 but positive 0.25 volts. And then we get a final answer of plus 1.05 volts. So you can see we have a positive value, so that reminds us that it is in fact a galvanic cell. So taking a look back at our diagram, we can now put in the direction of the flow of electrons. We can put in a few things. We can say that the voltage is going to read 1.5 volts here. And since the nickel is what's losing the electrons, the electron flow is going to start here and it's going to continue over to the silver electrode because the silver ion is going to end up being reduced. So wherever the electron flow initiates, that's going to be our anode. Whatever's oxidized is our anode. And then the cathode is the other electrode that is being reduced. So here we did a picture and we calculated our cell potential. This slide summarizes the difference between a positive cell potential and a negative cell potential. As we've already kind of talked about, a positive cell potential means it's spontaneous reaction. It's going to occur without any outside intervention. It goes by the term galvanic or a voltaic cell. They can be used interchangeably, and it takes chemical energy and converts it to useful electrical energy that can be used to do work. A negative standard cell potential means that the reaction is non-spontaneous. It is referred to as an electrolytic cell, and you're doing the opposite here. You have to put work in order to convert electricity into chemical energy. So one quick note, if I called a positive E cell spontaneous, that means that it's going to correspond to a negative delta G. And then the reverse is true over here. It's going to correspond to a positive delta G. So there's actually a relationship, and it's an equation we're not going to get into this year, but there's a relationship between Gibbs free energy and standard cell potential. This will be our last example, so you can pause it and copy down the green reaction. And then when you're ready, you can look up which half reactions we'll be dealing with on your reference sheet. So it looks like we're dealing with cadmium, and then we're also dealing with copper. And be careful, it's going to copper +1. So there are a bunch of different coppers you can pick from. Make sure you get the correct one there. So don't simply take a look at this and say, okay, well, copper is the more positive, so that's the one that's going to be reduced. You have to do it based on the reaction that you see. So if you look at copper, it goes from the metal to having a +1 charge. So that means it's going to lose electrons, and that's what's oxidized. So the reaction tells you what's oxidized. So the fact that this is oxidized means we're going to make this a negative 0.52 volts, and this arrow will be going in the opposite direction. So negative 0.52 volts is our oxidation potential. And then our reduction potential, the cadmium 2+ is going to be reduced. So it goes from cadmium 2+ and it gains electrons to get to cadmium metal. So even though here we have a 2+ and here we have a 1+ charge, we don't multiply through by moles of electrons. Remember, we're talking about like the pull of electrons when we're talking about cell potential. So that's independent of the number of moles of electrons transferred. But the good news here is that we can take this value straight off the reference chart because it's already in its it's already written as a reduction potential. So that's going to be negative 0.40. And then when you add these up to get the overall cell potential, standard cell potential, just add them up. It's going to be a negative 0.92 volts. That negative implies that it's a non-spontaneous reaction. So this would not be an example of a galvanic cell. It would be an example of an electrolytic cell.